Okay, we're continuing our series with these note cards of electrical engineering and circuit theory. So finding at Thevenin resistance. So Thevenin was this guy who thought about, okay, what if we have this black box, this circuit, and we want to know its internal resistance for impedance matching or something like that, but we can't take this box open. So he came up with this whole process here, which is isolate the load. Let's say, for example, here L is our load. It happens to be an inductor, but it could be a resistor or a capacitor or any combination thereof. So you want to have these two open terminals here. Then if you have a voltage source, you want to short it. If you have a current source, which is something else that one of these other cards might get into, a current source, then we want to find the resistance or the impedance across the two terminals where the load goes. So let's say here, for example, we have E, this is our voltage source, we have this resistor, we have R1, we have this R2, we have this R3, and we have a current source over here. Voltage means the voltage is constant, but the current depends on the draw. A current source means that the amount of current is constant, but the amount of voltage is may not be constant, essentially. And so if we have a short circuit where our voltage source was, and we have an open circuit where our current source, the little funny arrow there, was, then our Thevenin resistance where our load was is, well, now this is an open circuit, which means there's no current here. We just have R1 essentially in parallel with R sub 2, and then that is basically our Thevenin resistance. So that is just an example of how RTH or RThev works here. And then once we have the Thevenin resistance, there's Thevenin voltage here. So find RThev and put the voltage or current source back into the circuit. Then find the open circuit voltage across the load terminals. So there will be volts but no amps. So here, so we have 9 volts and 3 ohms, and then 6 ohm load. So we find our Thev, so we have 3 in parallel with 6 ohms. This is what we just saw, find Thevenin resistance here. And then we put the voltage source back in with our 6 ohm, which is our Thev here, and now we find the voltage across those 2 points, and this is basically becomes what is known as a voltage divider. And so we have E Thev as product over sum, so 6 volts here, and we end up with our Thevenin equivalent voltage source of 6 volts here and 2 ohms here. So yeah, that's kind of too fast to really go over it, but we'd be here all day if I did that. Anyways, another method of circuit analysis is superposition. So when there's more than one power source or more than one frequency, pick a source or signal to solve for. Make the other sources dead, which is to short your voltage source and open your current source, and then add the results of each analysis to get the final value. But it can't be used for finding your power in watts. It can be used to find your voltage or your current. Then we have this deal with what we call maximum power transfer, which builds on that. See, in this diagram we have your E Thev and your R Thev, and then we have your load, which is drawn here as a variable resistor, and max power transfer is equals when the load, R sub L, equals your Thevenin resistance. And here we do get into some power calculations here. See, P sub R sub L, the power of the load resistor is I squared R, which, and then your, well, and I squared R is one way to find power. The other way is V squared over R, and then just simply volts times amps, or V times I is your power in watts. And as you see, you get the max power transfer when your slope is 0. And then we have your current, which is I equals E over R. In this case, the R is the sum of your Rth plus your resistance load. And for reactive elements, the load is the complex conjugate of the source. And what complex conjugate is just 10 ohms plus or minus J20, which is, or it becomes minus J20. You just change the sign from positive to negative. That's where we're going to get into complex numbers. Mathematicians and a lot of the other non-electrical world uses I for your complex coordinate, or your complex plane. But because I is used by electrical engineers for current, we use J for our complex number identifier. So, getting a little bit more into alternating current now. We have an AC voltage divider, as we just saw briefly. The voltage divider, V sub X, is the voltage of Z1 or Z2 across one of those two impedances. We're going to get into impedance recently. Impedance is an alternating current term for resistance because it has not only a magnitude, like say however many ohms, it also has an angle because a sine wave is a rotating vector, and we'll get into that. So E is your AC voltage peak, and your Z sub T is the sum of your impedances. So there's your little formula for an AC voltage divider. Now, not only can we divide a voltage, we can also divide current. As you saw, we just had impedances in series. Then we have the impedances in parallel. Say we have the product over the sum, but it's the product of Z sub 2 multiplied by the total current. That's your product, and then the sum is the sum of the two impedances. So, current of an element is equal to the product, the total current, times the known impedance of the other elements, divided by the sum of all impedances in the parallel circuit. We also have this thing called conductance. So conductance is the reciprocal of resistance. And resistance is, as a reminder, how easily electrons flow in a circuit. A resistor has some R number of ohms. It also has 1 over R mhos, which is just MHO, is just OHM, ohm spelled backwards. That's literally what they did until they found this guy named Siemens, S-I-E-M-E-N. He was a German guy, and you've probably seen his name on companies and stuff. There's a whole company with Siemens Electronics and whatnot there. They named the unit of conductance after him. And getting back, we not only have the Thevenin form of the signal source or some voltage detection here across the two terminals, but this is the Thevenin form of a voltage source. So we have our voltage source here on the left with some R sub S, which is the resistor for the voltage source, should probably be a low value because the voltage across the resistor is going to be equal to, well, D equals I, your current, times R, the resistor. So if it's, say, low, say close to just 1 ohm or so, then it will simply be the current. It's not going to degrade the voltage of the power coming to the source, but I go on too much. Okay. And we have the Norton form. And the Norton form, all that really is we just take that same source resistor, or a resistor, and we, well, getting back to the whole voltage divider idea, if we see the Thevenin form, if we place a load across here, we're going to get a voltage divider. So, with this being R sub 1, if this is small, then that means most of the voltage is going to go through here, and the current will be the same in the loop, same current in the loop. But most of your voltage will be across your larger load. But here we have basically Norton form sets us up for a current divider. And here R sub S should be a high value. So that means when we put a load across these two terminals here, then the voltage is going to be the same across two parallel elements. But in the Norton form of our power supply, we have a source of current, the same voltage, and so the current through a really high value resistor is going to be very low, because there's a lot of resistance. Remember, resistance is the it reduces the flow of current, and then there's going to be the most amount of current going through our load, and that's what we want in an ideal current source. In a perfect world, this resistor would be near infinite. So there's your Norton and Thevenin equivalent form sources.